Hello, everyone. This is John Avina. I'm president of Abraxas. You've probably heard me talk at one of these before or been trained by me or something like that. I won't introduce myself, but I will introduce Chris Christian. So Chris is one of our senior engineers, and Chris has been around probably longer than me. Actually, I think so. I probably get this all wrong, and Chris will interrupt. I've told him to. But I think he's been around for about 35 years doing HVAC, commissioning, M&V, retro commissioning, audits, you name it. And not only that, tab, but he started as an HVAC mechanic, a hands-on guy. So this guy, Chris, it's like you go into a mechanical room and you ask, what's that? And he knows. And that is really, really valuable. I've met a lot of good senior engineers where you can point at something and say, why is it like that? And they won't have a clue, but Chris does. And I don't know, this guy knows a lot, and I think he's going to be a great teacher for the next 45 minutes to tell us about chillers. I'm going to ask a few questions and interject and try to keep it at least at my level, which I'm thinking might be yours. But Chris, did I get anything wrong there?
Well, I told somebody the other day that when you're my age and you've been doing it this long, everybody's junior to you. So, you know, everywhere you go, everybody's younger than you are. So I guess that makes you senior. So, but I also, when I started out, everybody looked at me and said, he's too young to know this.
Yeah.
So I'm getting revenge and all that.
So, all right. So I guess really quickly, some of the topics we were supposed to go over, and we're going to go over, actually, when it comes to very basic fundamentals, like what does a chiller do, I think we're going to gloss over that because I think you know that. But what we are going to go over is some basics of, you know, what are the different types of chillers? I know you've heard of scroll compressors and you know, turbo cores and absorption and centrifugals and reciprocating and all that. Okay, that's all fine, and maybe you can identify all or most of those in the field. But the question is, why do they choose some and not others for this application or that application? That is useful knowledge to know what are the benefits and drawbacks of the different types of chillers. And also, sometimes how do you identify them quickly? You look at it, it's like, oh, that's that. And I'm hoping Chris is going to tell us all that stuff. We're also going to go over this concept of chill water, a low delta T. And why that's important. It's actually a pretty neat thing to know if you do energy audits and stuff like that. It's, you know, this can kind of separate you from a lot of folks who do audits who don't have a clue to look for it. And Chris will tell us about that. We're also going to look at primary, secondary, and primary systems and things like that. And then there's one other, and that was this whole, I don't know if this really comes up, but I thought it was amusing. It's the whole idea of saving water versus saving energy. There actually is a trade-off. You can save water or energy, and we'll talk about that as well. So those are the topics today, and we were going to start with some basics. Actually, I was going to start with the basics. As soon as it gets complicated, then it moves on to Chris. So what do we got here? Oh, I don't want to talk about this stuff. Chris, you can talk about this stuff. I don't want to talk about this stuff.
All right, so for those who aren't familiar with a chiller, a chiller is used to refrigerate water for its use in cooling for process systems, industrial, and for buildings. All it does is take heat from one water loop and transfer it to another, either to the air, just like your house unit, or to another water loop where it's rejected in a cooling tower. So that's just fundamental. Now, this slide shows the difference between the low side and the high side. The low side has the evaporator, that's where the refrigeration cooling happens, and the high side is the condenser where we reject the heat, and that's always common. But you have one side versus the other. We use the terms interchangeably, so we talk about high side and low side. It just means evaporator and condenser. So the types of chillers, and these are industry standard packaged air-cooled equipment, and they're very convenient. You can buy this package and you just pipe up the chilled water side to it. This is air-cooled. It rejects the heat to the ambient air through a condenser coil. You see these coils in that section along with the fans on top, or they're on the horizontal to where you can see them. The diagram on the left are rotary compressors. The picture on the right are reciprocating compressors, and we'll talk a little bit about those in a minute. The other option is water cooled, where you use in this case, you take the heat from whatever you're pulling it out of, the building or process equipment, pumped it through the chiller. The chiller removes the heat from the water, puts it into the condenser, which pumps into another loop through the cooling tower to reject it. These pictures show different machines, and we are equal offenders here. So there's a York in the middle and a Carrier on the right. But these require piping for both the chilled water and the condenser water versus the air cooled where you only have the chilled water loop. Now we're going to talk about a little bit about the third option, but these are not as prevalent. You don't see a lot of these, but it's absorption. Basically uses the chemical properties of combining chemicals in the evaporator to refrigerate, and then it causes them to boil off the refrigerant, refrigerate the water. It then uses a heat source to separate those chemicals in order to regenerate and recycle them back through. These were very popular back in the day where you did not have as great an electrical infrastructure or as much power generation as we have today. Plus, if you had a factory or somewhere that you had a lot of waste heat, these would really be good because they use heat to operate. They have to have a heat source in order to drive off and separate those chemicals and recycle them. So if you had a manufacturing process or a plant that used a lot of steam or combustion, or you were out in the middle of nowhere where you didn't have a lot of electrical power, or you only had a generator that only had a certain capacity, and you needed chilled water, then this was an option, because if you had a ready source of free or sideline process heat available, like on a ship. They used a lot of absorption on naval ships because they generated steam for propulsion, and so they used the steam also to generate cooling. These are not as popular today because of the cost of generating heat, but they are still around, and we're not going to spend a whole lot of time on them. They're very specialized and complex. They are ideal for if you have waste heat and with a limited electrical supply, and their plant efficiency is rated in COP, coefficient of performance, where you compare the BTUs produced by the BTUs consumed. And so you kind of want to stay on a positive number, 3 or a 2.
I want to interject right here. So every once in a while we run across places where they have absorption chillers, and it just seems ludicrous. And you just not wonder, but it actually sometimes becomes an ECM to just get rid of the damn thing, that they produce steam only for the absorption chiller.
Right. And so that'd be a waste. They were very popular like in the 40s, 50s, and earlier. And so they gained a lot of popularity because either natural gas or you had a heat source available, and this was a sideline to produce chilled water. But nowadays, the energy costs so much, these are really bad as far as a new installation. I've had one here locally, and that's another thing. Climate has a lot to do with it. We had one here locally put in by a utility company for their robotics center. It's as a display, and it just did not work. It never did accomplish anything. Every time they held a conference there, everybody commented on how bad this system worked because it just could not keep up.
That's excellent.
So they have limited application. We had a university up here that had nothing but this. We've had churches that would buy them because they could not afford, or they didn't have the electrical infrastructure to drive chillers. The chillers use a lot of electricity, whereas if they were generating steam, they could use the steam for absorption. And so that's what they did. But as time went by, this thing became a dinosaur. And there it sits still. I bet you I could take you there now and you can see it just sitting there. So they've abandoned it in place.
So Chris, I ran across a hospital where they're talking about crystallization. I guess that you need a lot. You need to be on top of it on O&M to keep these things from breaking.
Right. That one I'm telling you about, the utility, the guy was telling me about the startup. They brought a guy in from New Jersey, and when they would turn the pumps on to get the flow going in the machine, you heard it sounded like it had rocks in it. because the solution solidified at ambient temperatures, and you had to drive and heat them up in order to get them to break down into a liquid. And so when you first started the thing up, it sounds like you're pumping boulders inside there. And he thought that there was something going wrong with it. The guy just said, no, that's normal. But yes, if you operate them over a certain amount of time, you don't take care of them, they will solidify into a brick. I mean, they will get to the point that they will not do anything, and you just ruin the machine. So we're going to talk mostly about the mechanical chiller cycle. This is a blow up of the previous slide. So you've got on the bottom half is the chilled water side, the low side. That's the parts that you're going to use the chilled water for. You transfer the heat out of the water into the refrigerant. The compressor picks up the gas refrigerant, compresses it to the high side where it condenses back into a liquid. And it's condensed because of that condenser water that you're going to reject the heat, either to a cooling tower or a reservoir, or in the case of air cooled, it's just the ambient air. Okay, so this is just a simple cycle. Chiller efficiencies are rated in their ability for energy use versus its refrigerating effect. And so we talk about tons and what a ton is, and chillers are rated in capacity for tonnage. A ton of refrigeration is the amount of heat absorbed by 2,000 pounds of ice, okay? It's 288,000 BTUs. But if you did that in a 24-hour period, you're removing 12,000 BTUs per hour. That is what chillers are rated in. So if you had 200 tons, you would have 200 times 12,000 BTUs would give you how many BTUs you'd move.
That's confusing. So how about let's just keep it simple. So the word ton seems stupid to me. It's like we're talking about refrigeration and they're talking about tons, and it's like you can't.
But
go ahead.
When we first started doing refrigeration, we had ice. And so they would send ships up to the Arctic Circle to carve up the ice floes and ship them back to cities like New York. Don't you remember the Iceman climbing up the stairs with a block of ice on his back?
That's right.
That's when we have, what is it called? It's this box with ice in it. It's an ice box. That's the only refrigeration people had in their homes. That was the only way that they could cool their food. You know, there was a big revolution when we came up with mechanical refrigeration that people could buy and put in their homes. Otherwise, they'd have to go down to the butcher, the locker plant, store their food in refrigerated storage, and they would have to go down there every day to go pick up their food that they had in refrigeration, because not everybody had refrigeration in the home. And so they would get these blocks of ice, ship them to those major cities, and then they would cut them up and sell them to you and everyone else, and they would melt the ice for refrigeration. That's the only refrigeration you had. So they calculated how much refrigerating effect a block of ice could do, and that is how we get this ton, because it's 2,000 pounds of ice being melted. That's the fundamental basic, that's where it came from over 100 years ago.
That works. Very good. Thank you.
Yeah, that's where we get the term. And we still rate the equipment and how much heat it moves. And in this case, it's going to be 12,000 BTUs per ton per hour. That's 1 ton, or 12,000 BTUs is 1 ton of refrigeration in an hour. Okay? So we use kilowatts per ton and how much energy we put in divided by the tonnage produced by the chiller. And we'll talk more about this later on, but it's power input to refrigeration effect output. The lower this ratio is, the better. 2 to 3 kW per ton. We'll take a look at that later on. Another way of rating how efficient your machine is compression ratio. Sometimes it's now being called lift. You know, when somebody says that, I look at them like, what are we lifting? But it's the difference between the high side and the low side pressure in absolute pressure, not gauge pressure, because a lot of machines work in a vacuum. They'll actually pull a vacuum on the low side. You need an absolute pressure in order to do the calculation. So we use absolute pressures to compare. Now, these can be 2 to 3 also. The lower the compression ratio, the better. That means that your machine's not working so hard to produce the same refrigerating effect. Then we get the coefficient of performance. We talked about that in the absorption side. We can do this comparison, but you have to convert power to power. So it's not a comparison of BTUs to power, or power to BTUs, like in kW per ton. It's instead, you got to compare BTUs to BTUs, input to output.
Yeah, I'd like to interrupt right here. So I think coefficient of performance, and maybe I'm wrong, but the way I've been seeing it, it's just like efficiency. You look at electric resistance heating and how efficient is it, or
Yeah.
it's 100% more or less. So
Yes,
all power ins, power out. And for cooling, if you have a COP of 3, it means that it's 300% efficient. It's going to move 300% of what you put in.
So like for heat pumps, you'll see ratios of 3 because the energy used to produce the heat is not an equal thing like your electric heat. So you actually are using less energy to produce more heat.
It's not produce, it moves heat. So you put
but you're
energy
generating
and you move 3 times more.
You're generating heat. In the case of a heat pump, we're talking refrigeration, that goes the other way, but you have to compare power to power or BTUs to BTUs to use COP.
Yeah.
Okay, so we're going to talk a little bit about compressors. Each one of these compressors has its own characteristics. The most fundamental is the reciprocating, and we talked about that when we looked at the air-cooled. You see a lot of these in low to medium capacities, 10 to 20 tons in a package. The advantages are that you can have multiples arranged to control your varying capacity. So from 100% all the way down to 5% of the total capacity, it can be built in an air-cooled package, shipped to the site. All you got to do is pipe up to it, fill it up with water, run the pump, and hook it up to electricity, and you're good. The disadvantages are, and reciprocating is not the most efficient compressor because it's having to deal with, especially in air-cooled, it has to deal with the ambient, and we won't get into too much detail. We might see a little more detail in the actual cutaways, but the higher the pressure it has to pump against, the less efficient it is. The harder it has to work to compress. And so in ambient conditions or air-cooled, the higher the outside air temperature, the harder it is to work. And so that loses its efficiency as the outdoor air temperature that it goes on air-cooled has to work against. It starts really eating up the energy. So the examples here, that's a cutaway. Those pistons compress the refrigerant in a cylinder, and there are valves at the top that either let the refrigerant in or let it go out. You see these in hermetic. Those are the ones, those black ones over on the right, or semi-hermetic, the one in the bottom right corner. That's serviceable. You can open up the compressors. That's actually an ammonia system. But the motor is separate from the compressor versus the hermetic there at top. If that motor goes out, you've got to replace the whole compressor. So in one case, your motor, if it goes out, you just replace the motor on the semi-hermetic or the open drive, and you can actually work on the compressor by itself. But in the hermetic versions, you have to replace the whole thing if something goes wrong. So the next upgrade would be the scroll. These are mating, rotating scrolls that actually compress the gas on the high side. One of them mates with the other, kind of what that middle diagram shows, the low pressure vapor and the high pressure vapor. This is an improvement because it reduces the inefficiencies of the reciprocating. They also come in a hermetic version, just like the reciprocating type. You can get them in a semi-hermetic version, but they're fundamentally a closed unit. But they are more efficient than the reciprocating, and you can put these on variable speed, whereas the reciprocating, you couldn't, because it's just like your engine in your car. The slower the speed, the less lubrication it gets, and it might seize up. So those run at constant speed. These, however, the scrolls, you can vary the speed because we're not worried about it. An upgrade also some years ago was the rotary. The rotary basically has one rotating cylinder inside another cylinder with these vanes that compress and isolate the low side from the high side. One of the problems, though, is the whole compressor is on the high side, and so they get very hot. So the early versions had trouble maintaining lubrication because it got so hot. The outside of the case, you couldn't put your hand on it. These were handy for small applications, but they also upgraded to large chillers and actually applied them there to where they could actually use them in chillers to move a lot of refrigerant, but they also had to manage that lubrication control. They had to cool that at the same time. So these are very effective though, because they are more efficient than the reciprocating, but you still have to manage them a lot better. Now we have kind of a marriage of scroll and rotary called the helical screw compressor. These are more efficient than the reciprocating. They're better efficiency in reciprocating versus in a variable speed application, and you can vary their capacity over a wider range with a single unit. You saw the comparison of the air-cooled reciprocating versus the air-cooled rotary. You had fewer compressors in the air-cooled rotary, helical screw, sorry. So you can actually do the same capacity with less compressors, but you also have better control over the range of capacity with these, because you can put them on various variable speed drive. They have very efficient compression ratios, and so they're just an upgrade on the compressor side from both rotary and the reciprocating. So now we get to the big boy. The big boy is the centrifugal. One of the differences here is that it works basically like a water pump, except it pumps refrigerant gas. It uses a large impeller that rotates at a high speed. The one that has the cutaway on the left is actually a two-stage. If you follow the piping, it takes in refrigerant gas on the left, compresses it out the top, and then pumps that into the intake on the right, which pumps it into the condenser. So it uses one motor to drive two impellers at a high speed to boost up the gas to condense it. But these are designed to move massive amounts of refrigerant. The kind of diagram here at the bottom right gives you an idea of what it does and the temperatures we look at. The temperature difference is at 10 degrees on the evaporator, the cooler side, and then it compresses up to 95, 85 degrees on the condenser water side. So these are typical of the range of operation for these chillers. And this is always the case where you rate the chillers and the cooling towers based on the condenser and how you size them. So, but they are designed to use move massive amounts of refrigerant. I've seen 8,000 tons in one machine. So they can do a lot of work. One of the drawbacks though for the other ones, the early ones, was that you could not go to a low capacity. They had a lot of trouble going in low capacity without variable speed. They were a constant speed machine. You controlled the refrigerant flow by inlet vanes. And if you got down to a certain point on low capacity, they started having trouble called surge. So you're basically starving the pump, the centrifugal machine, and it sounds like it's gasping for air, and you can actually hear it. And so I've been doing this so long, every time I hear that noise, I know exactly what it is, and I start to worry because it's either going to shut itself down or some damage may happen. You also get the same problem on the high side. If it's trying to push against a high temperature, it will push the refrigerant backwards. These are non-positive displacement. So if you have any trouble either on the suction, the inlet side, or the outlet side, refrigerant's going to get pushed backwards through the impellers and they will scream, they will make a noise. Whereas all of the compressors we saw before are all positive displacement. The refrigerant can only go one way, in to out. These, however, there's nothing dividing them except the speed of the machine. And if you run into problems, it will blow refrigerant backwards and it sounds terrible. So an air-cooled, a little more detail. We're an equal offender. This is a trained piece of equipment. Rejects the heat from the system to the air on the condenser side. It's dependent on the air's ability to accept that heat. So 75-degree day, no problem. We're going to blow air across these coils and we're going to pull all the heat out of the refrigerant and condense, and we got no problem. But 105-degree day, it's going to be tough because you've got to get the refrigerant up above that to reject the heat to the air. So the higher the outside air, the more work we're going to have to do no matter what. It increases the energy. I mean, that's one of the things we're going to talk about, and we'll do actually an example to give you an idea of what's happening. For example, we got a 70-pound low side on the evaporator at about 85 psi. Then condenser pressure at 95 degrees outside runs about 250 or 265 psi. The compression ratio, you just do simple math, is about 3.11. Now, we go from 95 to 105 outside. Your high side pressure increases to 332 psi. And you do the math again, you're still trying to maintain the low side at the same temperature because you're trying to produce chilled water. But your high side is increased to 3.9. That's almost 25% increase for a 10-degree temperature increase. Also, one of the biggest problems we have is maintenance on these. We have to keep those coils clean. And if you get any kind of like newspaper or plastic shopping bags or cottonwood or anything else getting into those coils, it's going to decrease those coils' ability to reject heat, and you've got to clean them. That's a maintenance issue that's constant. Also, the wonderful children who go by a chiller who's sitting on the ground and carve their name into the fins has an effect also. And I mean, it's ridiculous, some of the things. I've had to spend hours combing them out. I also used to use a chemical cleaner to clean them, to acidize and try to get the garbage out, and I actually lost my fingernails because I used it. I spent all day on this thing, and the chemical got all over me and everywhere else, and I didn't know it was going to be that bad. But it's a maintenance problem that has to be maintained. But if you have to keep those coils clean, that's the biggest maintenance issue with air-cooled. It's a fundamental system. This is a constant speed, constant volume system using an air-cooled chiller. In a constant speed, constant volume system, you've got to keep the flow up. So we use three-way valves on all of our cooling coils. In other words, the valve either puts the water to the coil or it has to bypass and mix going back to the chiller to keep the flow up in the system. So these were typical of systems 20, 30 and older years ago, before the advent of variable speed. So we talk about water cooled. It required a second loop to pipe up the condenser water loop. It takes advantage of the evaporating effect of water to reject heat in large quantities. So when you see centrifugal machines, it's rare to see a centrifugal on air cooled. I have seen one. There was actually an R12 machine. That'll tell you how far back that goes. Package centrifugal air cooled chiller. It had a little control room. It was almost like something that you could put on the flatbed and drag out to a job site. But it was centrifugal and air cooled, and that's the only one I've ever seen like that. Using large amounts of refrigeration, we've got to reject the heat in large quantities. So we need water cooled to do that, and we use the evaporating effect of water. So here's a typical system. Again, we're constant volume on both sides. So we pump the water through the chilled water loop into the evaporator. It picks up the heat out of the water, transfers it to the condenser where we reject it to the cooling tower on the outside. Now we start talking a little bit more about our chilled water systems. This is constant speed, constant volume. It's the simplest system out there. You're going to see a lot of these still in operation, not so much in new buildings. So the older buildings will probably have this operation, and if you want to convert them over, you can do that, but you've really got to watch your machines. Chilled water is pumped at a constant speed. The condenser water is pumped at a constant speed. It requires a full flow at full capacity through the system, no matter the load. So you're pumping the same amount of water all the time, no matter what kind of load you've got in the building. Your chiller then has to be able to change its capacity to meet those demands on the system. This is where we get into the issues where we're pumping a lot of water and we don't have a lot of load, so we get a low temperature difference on the chiller. And it has to be able to handle that low load. So now we start getting into variable speed. We can have variable speed systems where you can vary the chilled water flow according to the load, but the chiller has to be able to handle it at low flow rates. So you can have a combination of two-way valves and three-way control valves. Three-way control valves provide the minimum flow path. I've actually seen buildings where they have one three-way control valve that was sized large enough to where it could provide the minimum flow to keep the chiller online. And so when it modulates, it gives the water a path to travel back to the chiller without interrupting it. Otherwise, if you had nothing but two-way valves, you would deadhead or block the pump. you would resist the flow of water and eventually get below the chiller's ability to stay online because the flow got so low. Nowadays, with the advent of variable speed drives, we put variable speed on both chillers, pumps, and everything, that we can maintain the flow through the system by the use of a decoupler. This way that we can pump water, and if you notice, these are primary only so far. We only have the one chilled water pump. We put a variable speed drive on it, we vary the flow through the system, but what happens is we can actually control the low flow by a bypass valve through a decoupler pipe that allows me to bypass the flow to maintain the minimum flow for the chiller and keep it online. We actually have a flow meter in this system. And if the load, the coils out there need water, they open up or close their two-way valves as needed. So we both control the amount of water we send out to the cooling coils, but we also maintain a minimum flow on the chiller to keep them on, keep it online, so it can stay. And if it has a very low turn down where it can go very low in its capacity, we can unload the chiller, we can unload the flow of the water. We're actually saving energy now to where we can match the flow necessary for the system to the flow necessary to keep the chiller up running its most efficient point. Sometimes we can put this decoupler at the end. I've seen these on the end of the loop to where you push water all the way out to the end and it bypasses all the way back. That way you ensure that you keep flow all the way through the system, all the way to the end. So the location of the decoupler is not critical when it's a primary only system. Now in this case, we have a primary, constant primary, and a variable secondary. So we keep flow the same on the chiller all the time, but we vary the flow going out to the coils. We still have to have a decoupler to make this work. However, because of the primary side, that pump will pump water to the chiller through the decoupler and keep that loop going at a constant flow. The secondary pump picks up water from the supply side and pumps it out to the system in whatever flow is necessary according to how many control valves are open or closed. And so you're able to maintain your flow on the chiller with the primary pump, but it's constant, and vary the flow to the load on the coils to use only as much water as you need. So you're getting some benefit out of that because you're not constantly flowing all that water throughout the entire system like you had with the primary only system, but you still are maintaining a constant flow on the chillers. So you're not saving as much as you possibly could. Now this is the ultimate of everything, a variable primary along with a variable secondary. Now both of these systems, the constant primary and the variable secondary, have issues that the operators may or may not understand. And so we're always constantly running into issues where they are complaining about something's wrong. This system, the variable primary and the variable secondary, take advantage of all the benefits you can get out of the chiller. Chiller can operate at a low load. Some of them can go all the way down to 10%. You can vary the flow on the primary down to that low, and you can vary the flow on the secondary. So everything you've got involved is saving energy by reducing the amount of energy you need to operate. So it can match the load on the primary to the load on the secondary. You know, you have to have a proper control strategy though to make this work. And the primary flow must match or be slightly higher than the secondary. Do not overpump the secondary, and that's where we run into trouble. We see this a lot. And here's an example. Here we have a variable primary running about 120 GPM. You got a 10-degree differential across the chiller. It's running around 50 tons. Its design is 100 tons, so we're running 50 tons over here. It's half of the flow. However, somebody complained and said that they weren't cooling very well, so somebody upped the flow on the secondary. They increased the flow on the secondary to 100 GPM, 180. So now the secondary is pumping more water than the primary provides. And so what's happening, you've got flow going backwards through the decoupler. You're mixing the 52-degree return water on the building with the 42-degree supply water coming from the chiller, and you're in 45-degree water going out to the coils. Will it improve if you keep running it like this? if you keep going, this imbalance between the two flows, your load will get worse. You're putting 45-degree water out. Let's say you go up to 200 GPM, because after all, the valves are opening up on the load. You're just not getting the cooling you need because you're running 45-degree water instead of 42. So you're going to increase the flow, but nothing's changed on the chiller. It's still running at a 10-degree differential. Now that though it's 55-degree return, you get a 45-degree supply, but now you got 80 GPM going through the decoupler the wrong way. So now instead of 45-degree water like you've got coming out of the chiller, you've got 49-degree water going out to the load. You're actually reducing your tonnage available to the load, the more water you're pumping in that secondary. So this is, again, is why you cannot overpump that secondary, because you'll mix the water with the return water with the supply water going out to your load. You don't want to do that. You want to mix the supply water coming from the chiller with the return going back to the chiller to unload the chiller. Chiller hasn't changed a bit, but your load is increasing out there on the system, but you don't have enough cooling capacity to cool the building. It's just going to get worse.
That's great, Chris. Yeah, let's do this delta T, the low delta T.
Yeah, so here's low delta T. This is one of those things that's, if you notice in this one, the flow rate's constant. So this is constant primary system, but a variable chiller. Chiller is very good as far as getting down to almost 20% of its load, but its highest efficiency ends up here at 50%. That's the kW per ton column. It's a 0.386. That's its most efficient operating point. So this is where it's critical to figure out what your load profile looks like on your building. The chiller actually operates, though, most of the time in the 75 down to 60% range, not the most efficient point. They are actually increasing to 0.43, 0.96, 0.53 kW per ton. Also notice the entering chill water and leaving chill water. It's trying to maintain 42 all the time, but your delta T is going down. So this most efficient operating range is between like a 9 down to a 7.2 degree delta T. But its most efficient point is 6. Then we start looking at unoccupied. You have very low load, but you're running 24/7 on this chiller, and so its efficiency on low load is not so good also in comparison to its most efficient operating point. And there your low delta T's are showing up. You have a constant flow on the primary of 900 GPM, and you're getting down into the 3.6, 3 degrees, and 2.4 degree range. That's where your efficiency goes up. You're running, it takes more energy to maintain this low load than is practical. So in this case, they're operating on both sides of the most efficient point. And really, if they'd have resized the chiller, they probably could have dialed it in to where you get all these hours of run time in its most efficient point. But in this case, they're bracketing above and below. So I guess they took a shot, put in a chiller that they thought would be most efficient based on those hours. It's obviously going to run between 75 and 25%, but that's maybe not the most efficient point. And then we get into this term of non-standard part load value. That's the rating that tries to compare the entire operating, the efficiency of the chiller based on a non-standard load. It's this varying load. And so we use this number a lot to try to figure out if this is the most efficient operation or not. In this case, it's 0.4242 on this machine, which is actually below its 60% load. So if you could maintain that 60% load or at that 0.442, that would be good, because that would be kind of an average on its non-standard part load value.
Chris, I'm a little confused here. So now you can't maintain a load of, let's say, 60% or 50% unless it's always hot and there's always people in the building, right?
Right.
I mean,
right.
You can't just, decide that we're going to work 3 shifts so I can be more efficient.
Right. So this is where the selection of the equipment is critical. It's rare that you get to 100%. And in this case, the client said, yes, on Monday morning we might load up, and then it'll run like that for a couple of hours. So you're not at its most inefficient point. It's where it's running most of the time is where you need to get the best efficiency. And in this case, 50% is its best efficiency, but you're running most of the time 60% to 75%. So if you had this data when you were designing the system or coming up with a solution, this is where you'd look at the most efficient point at 70%. I would rather have its best efficiency at 70% because that's where I'm going to be running most of the time. Either that or break up the load into different size machines that run most efficient for longer hours. This is one machine, and so it's the only machine that they run, and it has to cover this capacity high to low. In this case, it gets down to 90 tons, but I don't think I want to run at 90 tons for a long time. And I certainly don't want to run at 80%, 360 tons for a long time, because the efficiency goes down as I increase my load. So this is where you start looking at this data from the manufacturer and say, okay, is this the right machine for me? Or is this the right machine for my solution?
But that's all, design and stuff. For people who are going in and doing audits or looking to see, why is a chiller not as efficient as we thought it was going to be after we installed it.
Right.
Now, I thought, and I guess I was totally mistaken here. I thought that the whole idea of low delta T is it has to do with chill water flow, and that you can.
Well, in this case, that's the issue.
Okay.
This is constant primary. They have a constant flow on this chiller all the time.
Exactly. So if you are able to, if you have a low delta T, then you want to decrease the chill water flow so you can have a higher delta T, and then the chiller will run more efficiently.
Yes, and so that would push this efficiency into closer to more efficient operation with a higher delta T by lowering the flow. And this machine will do it. It's just that they didn't do it.
Okay, so if we're out there doing audits and stuff, and we look at the chill water supply and return, we have trend logs and all that stuff, and we see that they're often at 3 degrees or 4 degrees. Yeah. It means there's an opportunity, and let's say there is a variable, well, no, maybe there's not a variable frequency drive on the chill water pump, but that means that there's an opportunity for savings.
Exactly. Yes, and if the machine will handle it, this machine will handle it, they just didn't do it.
Okay.
And that was their complaint. The NEBB company, the company that did the job, was trying to figure out why they weren't running it more efficient. And it turns out it was this flow issue.
So another question, I guess it's related, and again, I may be mistaken, but I thought, I don't know, but I thought a sweet spot in general for chillers was 10 degrees. You were looking for a delta T of 10 degrees.
Right.
And so if we had a delta T that was below 7 or so, we would start thinking, well, maybe it could be more efficient. Is that?
Yeah, in this case, in this case, yeah, if it was 7 degrees, in this case, the most efficient point is 6 degrees.
Right.
And so that kind of goes against that. If I could maintain a 10 degree delta T with a better efficiency, I'm going for that. Mm-hmm. In this case, they're looking at 12 degrees at the maximum capacity. We never reach that. And this building never gets that load. And so this kind of overkill. So we may not have the best option, and this really cries out for variable flow.
Good. Let's see. So I guess it's getting late. So I want to go over, there's one other thing, and that was, and I think this is common knowledge that when you have a water-cooled chill water system, the cooler, to a degree, the cooler the condenser water you can introduce, the more efficient the chiller is going to be. So you want to, that's why people do these condenser water resets so that they can have cooler water. And again, the chiller is more efficient to a degree because chillers can only handle, a condenser water temperatures of so low a temperature.
Right.
But so I just want to tell a quick story. I was doing an audit of a facility out in Idaho, and this is for the government. And this guy, I was asking him, why do you have a condenser water reset some months and not other months? And he said, well, I understand that if I have colder condenser water, I save energy. So that's what I do because I have energy savings goals. But I also understand if I have colder condenser water, I'm going to do more of it. There's going to be more evaporation and I need more makeup water. And I have water conservation goals too. So he would save water for half the year and he would save energy for the other half. And that way he was actually trying to meet both goals. I just thought that was an amusing story.
Yeah. Well, and that's another issue. You can vary the flow on the condenser, but there's a low delta T issue there too, because if you're running a high flow on the condenser, you can get a low delta T, and the chiller will not be as efficient because you're not removing the heat at a good rate and evaporating it at the tower. If you had 75-degree water coming in and 78-degree water going out to your tower, you're not going to evaporate as much at 78 degrees. But if you had 75 in and 85 out, you can actually cool the water faster and reduce your flow. So you're going to evaporate more water, but you're not going to pump as much to do the same amount of work. And in some cases, it really does have an effect on its kW per ton because the chiller is running at the same energy level, but not rejecting the heat as much or as fast. So you can save some pumping energy and improve your efficiency on your chiller by reducing the flow on the condenser side, but you've got to watch what you're doing.
Good. So it's time to answer questions, and I'm going to read one. It says, what parameters do you use to control the primary pump and secondary pump on variable primary, variable secondary systems?
So it's basically on flow. If you can read your flow, and I've seen this more often with like data centers where they have that exact arrangement where they have a bypass valve in the decoupler, they'll measure the flow on the chilled water plant and match that flow on the secondary loop, or vice versa, which is probably more accurate, is to maintain a differential between the two loops no matter what. So if you had 200 on the secondary, you want 250 on the primary. So it ensures that you're going to control the flow the right way. Another job that I saw where they didn't do that, they instead had a temperature sensor located where the secondary picks up the primary supply to make sure that the temperature coming out of the chiller and the temperature going out to the building was the same. And so they would either speed up or slow down the primary to maintain that temperature going out to the secondary. So that's a simpler operation, but you got to know that if I got 42-degree water coming out of my chiller, I want 42-degree water going out to the secondary loop. If I had higher than that, that means my secondary loop is pumping too much. So some cases they'll have a pressure differential on the secondary to control the secondary pump, but then something's got to speed up or slow down that primary to match it, to get the right flow. And that's a simple solution, is the actual temperature of the water going out on the secondary to match that temperature coming out of the chillers. So you can use flow or temperature.
I'm going to ask another one. So here's one. Do you agree with placing some type of control valve in the decoupler to prevent excessive bypass?
It's a good idea. It costs money. And I mean, these decouplers can be 10 feet long or 2 feet long. And you may not have the space to put something in there. I like it because it gives me more control. Some in the early days when they first came out with these, it was primary in and primary on the secondary. I mean, constant speed primary, constant speed secondary, and two-way valves out there causing the water to flow a certain way. They would just stage pumps on and off. But they had a flow meter in the decoupler, they had a control valve, and they had a flow switch to tell them which direction the water is flowing. And so that would either stage up the chiller, it would bring on more pumps in the primary, bring on more pumps in the secondary according to which direction the water was flowing and how much in that decoupler. And so that was one way to do it, but a control valve allows you to control the flow on the primary and have a response for the secondary to either increase more water to the secondary or decrease water to the secondary, but it will not prevent the water flowing in the wrong direction. Okay, the only way you can do that is by matching flows or, increasing the flow on the primary.
Chris? This is a really nice job. You made that really clear. That was good.
Thank you, everybody, for showing up. We'll see you guys next month.
Thanks, everyone.